All right, well, welcome everybody to the AERA SIG Complexity Theories in Education Summer Webinar for 2022. Today we're going to be talking about complexity-informed analysis of large and multi-level data sets, methods, and practical insights. And before we get going today with our two wonderful speakers, I want to give you Oh, a very quick overview of who we are. The Complexity Theories in Education SIG. This is your executive team here. So myself, I'm Joanna Garner. I'm the chair of the SIG from Old Dominion University in Norfolk, Virginia. We also have Dr. Heather Williams, who's our program chair from Boise State, Dr. Gwen Marchand, our secretary treasurer from UNLV, and then we have our fabulous webinar host, Serena Cinnamon from UNCP, and we have a graduate student representative as part of our team as well, Joey Eisman from Temple. So we're a SIG within the AERA organization, which is the American Educational Research Association. If you're not already a member of our SIG, please consider joining. We also have a Facebook group that's also titled Complexity Theories in Education. You're welcome to join that. So today we're going to hear from two guest speakers. Our first guest speaker is Dr. Jonathan Hilpert. He's the director of the UNLV Office of Learning Analytics at the University of Nevada, Las Vegas. And I'm going to read his esteemed bio here for you all. So Dr. Jonathan Hilpert is an associate professor of educational psychology and learning analytics in the Department of Educational Psychology and Higher Education at UNLV. He's the current director of the Office of Learning Analytics, which is housed in the College of Education. His research interests include student motivation, engagement, and interactive learning, complex dynamic and emergent properties of educational systems, and knowledge construction of complex scientific phenomena. His research on student learning has been funded by the National Science Foundation, as well as several internally funded research awards. His research findings have been disseminated in national and international education and psychological journals, including Educational Psychologist, Psychological Inquiry, Motivation and Education, Educational Psychology, Journal of Engineering Education, Journal of Women and Minorities in Science and Engineering, as well as presented at national and international conferences, including the American Psychological Association, American Educational Research Association, European Association for Research in Learning and Instruction, American Society for Engineering Education, and various symposiums organized by the National Science Foundation. Dr. Hilpert has expertise in a range of research methods with a particular focus on the collection and analysis of time-intensive and relational-intensive data for enhancing learning and instruction through the use of analytics. He also has expertise in a variety of quantitative and qualitative techniques, including structural equation modeling, hierarchical linear modeling, longitudinal growth curve modeling, measurement and assessment of latent constructs, thematic analysis, network analysis, and time series analysis. Dr. Hilpert provides leadership at the national level, having served as APA Division 15 Treasurer, AERA Division C Section 1E Engineering and Computer Science Section Chair, as well as President of the Scholarly Consortium for Innovative Psychology in Education, SciPi. Dr. Hilpert was hired at UNLV in the fall of 2019 after holding positions at Georgia Southern University and Purdue University. He earned tenure and was promoted to the rank of associate professor in 2015. He has taught graduate and undergraduate courses in topics such as learning theories and applications, research methods, statistics and assessment, thinking and problem solving, interactive learning, and motivation and self-regulation. He's also a pioneer and a cheerleader for us within the SIG Complexity Theories in Education. So with that, I'm going to turn it over to John.
Well, first, let me say, Joanna, thank you for that very generous introduction. I appreciate it. I'm going to share my screen here. dominant approach. So within a component dominant approach, the log of a click or that event could be interpreted in a defined way. So if a student clicks on the calendar, then we would make an inference and we would say, well, they clicked on the calendar, so they're obviously planning, right? And so we would take the click and we would translate it into a construct like planning that's associated with like self-regulated learning. Or we can take an interaction dominant approach where instead of looking at, counting up the frequencies of how they, of the things that they click on and say documenting how many times they've planned, we can say, well, maybe a student clicks on the home page and then they go to click on a quiz and then they go back and they click on a course calendar. And we're looking at the patterns or the sequences in the ways that they've clicked through the various elements within the LMS. And we're examining the relationships between those clicks as opposed to the clicks themselves. And that's the critical part, right? We're interested in the relationships or the ties between the variables, not the variables between themselves as our primary object of study. So we took a whole bunch of time series data that were records of student logs within a biology course, and then we analyzed them using a Markov approach, and I'll explain that in detail here in a second. And what we wondered was, do patterns in student click behaviors predict final course grade over and above prior course performance, measures of motivation, expectancy, value, cost? We're just kind of wondering, if we make meaning about the sequences in these click behaviors, are we going to get a lot of bang for our buck when it comes to trying to figure out whether or not these things are related to final grade? And then we want to know how central are patterns in student click behaviors to like a motivated learning psychological system? Are they deeply intertwined with conscious motivated processes, or are they maybe more associated with unconscious automatic behavior or automated behavior, automaticity? So we go through a series of analyses with some example data later on in the presentation where I answer these two research questions. So let's move into some of the methods that I've been using to analyze this click behavior. First, we'll start with the data collection infrastructure that we've developed on campus here, so I can just give you an idea about how we're gathering this data. So through our NSF-funded grants, we partner with a series of biology instructors, and they allow us to integrate quizzes into their courses that are essentially surveys. So students log into quizzes in the course, and they take surveys, and then we capture those survey responses. And then we also extract their LMS click events through the request table in Canvas. And all of those data are housed in AWS because Canvas is partners with AWS. And then we extract those click events from AWS and we store them on campus at the UNLV data center. And then the Office of Information Technology provides all of those click behaviors in a data lake for us that we have access to. And then within my office, more generally, we use the responses to those surveys and then also the click records to develop early warning systems, to assign interventions, and then also to develop data dashboards to support students and instructors. So the way that works is OIT develops a university data lake and provides us with an independent server, some independent server space. And then we manage the transformation of the data and applications that we use to analyze that data and then provide that data back to students and instructors. And then the Office of Online Education supports the development of like master courses where we integrate our quizzes and our methods wholesale into large portions of the curriculum so that we can kind of intervene with students early on who are having difficulties at important touch points within the university curriculum. And then also my office supports the research efforts and providing information back to the stakeholders. So when we go into the data lake, what we find is that we get these massive volumes of data. I mean, millions and millions and millions of rows of data for the courses that we analyze. And what we want to look through and how we define these click events is by looking at controller action combinations. So the data lake will provide information about whether or not a student has clicked on a portion of the LMS system, say like an announcement or submitted a document or contributed to a discussion, and then the action that's associated with that. So they may index a quiz, show a quiz, create a quiz, something like that. So what we do is we go through and we define combinations of controller or actions that are associated with the front end web page events. So we'll go through and we'll have research associates in my office click through a fake LMS core shell and click on everything within the LMS, and then we pull all of the log records from behind the scenes, and we go through and we triangulate what front end web page events are associated with which controllers and actions, so that we know what elements of the log record are associated with which types of clicks on the front end. And then so we analyze this data or prepare this data for analysis by using Markov modeling. So we do a kind of Markov process, and I define that as a stochastic process here. And I'll give you a better definition of this in a second. But essentially what we do is we take that time series data, that click sequence, and we transform it into a first order probability transition matrix using the Markov chain fit package in R. And then from that probability transition matrix, we can transform that into a data frame, which is essentially just a network object. And then we calculate the qualities of that network object. So we calculate the number of nodes, the number of edges, the density of that network, and the transitivity of that network. And I'm going to show you a picture here that's going to give you a much better idea about what I mean by all of that. So here, for example, we have a very simple time series data stream. So at 1 p.m., the student clicks on the home page. At 1:01 p.m., they click on the calendar. At 1:02 p.m., they click on the module, and so on and so forth. And so what the Markov process does is it calculates the probability of transitioning from, say, the home page to the calendar, right? So here we have one instance of transitioning from the home page to the calendar, and then we have another instance down here of transitioning from the home page to the calendar. And so for every instance in which the student visits the home page, 67% of the time they have moved to the calendar, right? So we go through and we calculate all of the probabilities of transitioning from one element of the system to another, and we create an adjacency matrix that describes all of those probabilities. So there's a 0% chance that a student, when they click on the calendar once, will click on the calendar again. There's a 67% chance that when the student clicks on the calendar, the next thing that they're going to transition to is the home page. There's a 33% chance that when a person clicks on the calendar, they're going to go to a module next, and so on and so forth. We take this probability transition matrix and we turn it into a network where the edges are the weighted probabilities of transitioning from one element of the system to another, right? So you can see that all of the cells in this probability transition matrix are now weighted edges within this network. And that's the simplest explanation I can give you of the Markov process here. And then what we do is we calculate the number of nodes, so that would be 3. So let's say there were 20 possible elements within the LMS system that the student could click on. This student clicked on 3 of them, right? And then the number of edges. So this network has 6 edges, 1, 2, 3, 4, 5, and then 6 with the loop back to the module over and over. The density, or the proportion of the potential edges that were observed versus the portion of potential that were observed versus the number possible. And then transitivity, the overall probability of having adjacent nodes interconnected, i.e. in a triangular fashion, and we call that transitivity. So that would be the number of triangles. So for example, going to the home page to the calendar, and then from the calendar to the module, and then that was a bad example, then the module back to the home page, but that doesn't exist as a complete triangle in this data set. But we want to know the number of complete triangles that were observed versus the number that were possible. And then so here's what one looks like. This is for an individual student. And so we calculate a network of click events for each individual student. And then here are some specific definitions. So we look, like I said, the number of nodes, the number of edges, the density of this network, and the transitivity of this network. And then we can use these statistics as predictors of whether or not they're going to perform well in a And then we just do that in R, like I said, using the Markov fit and the StatNet packages in R. And so essentially what I do is I make a series of functions that look like this. So I'll just make an object that is a calculation of the probability transitions, and then I turn that into a probability, an adjacency matrix using the transition matrix function. And then I turn that into a network object using the StatNet package here. And then I can calculate the size of the network, and that's function 1. And then I do that for the edges and for the density and for the transitivity. And so I make a series of functions, and then I just loop those functions. You can see later on in the code, I just loop those functions using tapply through each system user. So then here I'm just going to show you some quick example data. We leveraged log data from a post-secondary biology course in the spring of 2020. It contained 257,000 logs from 226 students enrolled in a course, or an online course. That's a mistake. My apologies. The student log data was extracted from the data lake, and we classified those logs into 13 different categories. Those were 13 different things that the students could click on within the course. And then we calculated student final grades. That was their effort that was spanning weekly quizzes, regular homework, 4 unit exams, and a cumulative final exam. And then we measured student motivation using a validated survey tool that we've used a lot out of my office. And that's just, measures of expectancy and value and cost and self-regulated learning and self-efficacy and a lot of constructs that you're probably very familiar with that I don't really have the time to define for you right now. And then what we did was we fit a structural equation model to the data using JASP, which just leverages the Lavon package. And then in the model, we positioned all of the variables as predictors of final grade to answer the research question. And then we established covariances within the constructs, say all measures of cost or all measures of expectancy, but not between the constructs, say from click behaviors to cost. And then we also did a Glasso network analysis of the data just to examine the centrality of the click behaviors to the motivated learning system. And that's just, it's a network that you spin up based on the variance covariance matrix of the data. I can answer some questions about both of these techniques in the breakout rooms if you like. So here are the results, just some descriptive statistics. We use Fimmel to deal with the missing data. You can see that as expected, the log data or the click data produced a power law distribution, and then here final grade was our outcome variable, 4 exams, a final exam, and then here are all of our measures of motivation. So self-efficacy, metacognitive regulation, attainment value, intrinsic value, utility value, effort cost, opportunity cost, psychological cost, and then the size of our network, the number of edges in the student's network, the density of the student's network, and the transitivity of the student's network, all at the student level. And then so the results of the structural equation model were super interesting, controlling for all of the other variables. The 4 click behaviors were all significant predictors of final grade, and so was self-efficacy. None of the other predictors in the model were significant. So this is showcasing the importance of these click behaviors. And then here's our Glasso modeling results. You can see that we get 4 clusters, the exams. Here's our cost measures. Here's our value, efficacy, metacognitive self-regulation measures. And then here are all our click behavior measures. So we get 4 neat clusters. And then what you can see is that final grade is the most central node in the network, but that is closely followed by the transitivity of their click behavior. So whether or not they're showing pattern sequences in the way that they click, and then also exam 1, how well they did on the first exam was really important. And then another interesting finding is that in terms of expected influence, the number of edges in the network had the biggest influence on the system. So for example, if I were to make a tweak to the number of edges, that would have the biggest influence on all of the other nodes in the network. So just to, some implications. I'll start with implications for analytics. These click behaviors were significant predictors of course grade over and above performance and motivation, which is really interesting to me. We struggle with kind of how to interpret these for instructors, because they don't understand density. I mean, these are complicated constructs, so we want to translate them in ways that instructors can understand. So we're thinking about calling them things like breadth of engagement, depth of engagement, patterns of engagement, for when we visualize the results on dashboards, but we're still trying these ideas out. And we also think that we have a scalable and domain general method for integrating click behaviors into prediction models that's informed from an interaction dominant complexity perspective. There's also some implications for psychological theory here. These click behaviors appear to be pretty central to the motivated learning system. They're also orthogonal to measures of motivation with weak and non-significant relationships with the observed motivation data, which is really interesting. And we wonder if this means that they are reflective of automatic or unconscious learning processes that live at a different scale of analysis. Here's a peek at some results that come from another course that we just gathered this summer. This is a comm course. This is way different than a biology course. We get a very similar set of results where final score is being predicted by our click behaviors moderately, and then we have some weaker relationships between final score and motivation. But we have no positive and significant correlations between conscious motivation and the click behavior. So they're both significantly and positively related to final grade, but they're not related to each other, and that's a mystery to me right now. This also demonstrates the usefulness of interaction dominant approaches to understanding relationships within data. And I think it's a clear, application of complexity concepts that has practical implications for stakeholders, because we can take these results and we can spin them up into dashboards that we make that look like this. And I have some examples, like live examples of what these look like right now, but we embed these in Canvas, and then instructors can monitor the patterns of their students' click behaviors, and they can monitor their motivation, and they can assign interventions based on the patterns that they're seeing from their students. And all of this is informed by a complexity perspective. And then they may be able to look at the patterns in their motivation and their click behaviors, and then, suggest that they maybe attend their, like the Writing Center or the Academic Success Center or something. So that's all I have. Thank you so much for listening, and don't forget to join the AERA Complexities.
We got time for a question.
Great. This is from Helene. If you looked at patterns in click behaviors and whether certain patterns are related to better performance or motivation, or whether you could use patterns in click behavior in real time to
Thank you. And we're going to switch. I'm going to share my screen here. So, let's see. we're going to wrap up our webinar now. I just want to say a couple things. I want to say a huge thank you to our presenters today, John Hilpert and Don Gilstrap. Thank you so much for sharing your expertise and your research with us.